first time. You don't do it like this. Hello, Dinesh sir. Hello, Dinesh. Brother. Interview play on. Play on.
No, 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 sorry. It's okay. Fine. Hello. Can you hear me?
Yes, sir. Yes, sir.
Yes. So hope you can hear me and see me. I'm really sorry for the delay because
Good evening,
uh,
sir.
I thought it is 7 o'clock and I was on the way from my office to my residence. So yeah, good evening to everybody. I mean, yeah,
Good evening, sir.
yes. So shall we start?
Sir, we will start in 2 minutes, sir.
Sure. Okay.
Dr. Vinayak, good evening. I'm
Good
Madhavan.
evening.
I'm the head of the department.
Hello, Mr. Madhavan. Yeah, hi. How are you?
So fine, fine. So
Yeah.
thanks for accepting our invitation. Happy to have you.
No, it's a pleasure. Just it's a moment of time. I mean, it's a matter of time because yeah, it's a semester about to start and a lot of other things. Yeah.
When I'm just going through your website, saw that Paul's quote, you know, God made solids and surfaces were by
Spaces
devil.
were made by devil. Yes.
Maybe you can throw some light when you have your talk on this particular quote that
Definitely,
Paul said
definitely. In
that.
fact, I gave a talk in Mumbai University. There was some alumni program. I
Okay.
gave a talk. The talk was title was "Devil Lies in Defect."
Oh,
So, so it is. I'll tell you. I mean, in today's talk, why I'm saying that and why we should be interested in defects. Um, yep.
fine, fine, sir. Thank you. And you
Nice.
can see there in the screen Dr. Arulmoli, the convener. would like to introduce her. He is our
Okay.
faculty, and
Hello.
she is the women behind all these things, right?
Good.
Maybe she can say hello there.
Yeah,
Alumni,
I
you can
think you
unmute
said
and say hello.
maybe it's muted. Yeah, it's fine. No problem. So where I have been to Loyola, I think a long time back. I mean, 5 6 years ago, I actually came there for a personal talk,
Okay,
like
fine.
outreach talk. Uh, yes. Okay.
In,
So
in a,
are we good to start or?
yes, in
We,
another couple of minutes with the prayer song, we will start with the formal.
okay.
Yeah,
Okay.
maybe the formal things may take 2 3 minutes. We'll start.
Okay. So do you have research scholars in the department?
Yes, we have research scholars. 27 in numbers. We have.
Okay. Okay. They're affiliated to my University
They
of
are affiliated to
Madras.
Madras University,
I see. I
and
see.
it's women-dominated research scholars. Right, most of
That
them are
is
women.
true in most of South India, and it's good thing. In Kerala, particularly, it's even higher. I think.
Yes, it's 27 in number and 24 are women.
Good. Okay.
Hello, sir.
Hello.
Sorry to interrupt you, sir. Shall I start the meeting, sir?
Yes, please, please start.
Sir, I am
Creativity.
audible?
Yes.
Okay. Okay,
When you're
Setu.
audible, you can start, please.
Creativity is thinking up new things. Innovation is doing new things. By Theodore Levitt. Good evening, everyone, and a warm welcome to Eluci-Physics webinar lecture series. It's a pleasure to have each one of you here today. We have come together as a community of students, professors, science lovers, and physics enthusiasts who share a deep interest in science. Let us start the session with the blessing of God through the prayer song.
Bless the Lord, oh my soul, oh my soul, worship His holy name. Sing like never before, oh my soul, I worship Your holy name. The sun comes up, it's a new day dawning. It's time to sing Your song again. Whatever may pass and whatever lies before me, let me be singing when the evening comes. Bless the Lord, oh my soul, oh my soul, worship His holy name. Sing like never before, oh my soul, I worship Your holy name. You're rich to love and You're slow to anger. Your name is great and Your heart is kind. For all Your goodness I will keep on singing. 10,000 reasons for my heart to find. Bless the Lord, oh my soul, oh my soul, worship His holy name. Sing like never before. Oh, my soul, I worship Your holy name.
The Loyola Astronomy and Innovation Forum, founded by the students, aims to exchange ideas and knowledge, encouraging their analytical and creative thinking in the field of science among the enthusiasts. Since the last year, the club has been actively organizing various programs, both online and offline, and workshops, etc., to inspire curious minds, especially in physics. We extend our heartfelt thanks to everyone who has supported us in establishing and spreading the light of knowledge through this club. A leader is the one who knows the way, goes the way, and shows the way. I am pleased to invite Dr. J. Madhavan, the head of physics department, to deliver the welcome address for this auspicious occasion. Over to you, sir.
Yes, thank you, Professor Vinayak, the speaker of the day, Dr. Arulmodi, the convener, Dr. Dinesh, the student coordinators, and my dear participants. Good evening to you all. A few words about our speaker. He is an alumnus of IISc, and then the Inspire Faculty Awardee, Rising Star that is being identified by ACS. These are the few things which may tell you the caliber of today's speaker. We are happy that he is here. So I would, on behalf of everyone who are welcoming him, let me thank him for accepting our invitation and being with us. Welcome, sir. Thank you for being with us. Thank you very much. Thank you very much.
Thank you, first of all, for inviting.
Yes, thank you. Thank you and welcome, sir. And a special word of welcome to Dr. Arulmoli and Dr. Dinesh for coordinating this event, and also to the student coordinators and all the participants. Before I conclude, I have a request. If you switch on your video, we can see your faces, right, and document it. It's a request from my side. Kindly, the participants, please switch on your videos for just a fraction of minutes, right? If you could switch on your videos for some time, right? We could see your lovely faces, right? Please. So thank you very much, and over to the MC. Thank you. Welcome. And
Thank you, sir, for your words of salutation. The beginning is the most important part of work. So I would like to invite Dr. S. Arulmoli, the coordinator of the Astronomy and Innovation Club, to introduce our guest speaker.
So good evening, everyone. It's my great pleasure to introduce our guest speaker, Dr. Vinayak, for today's webinar series. So welcome, sir.
Thank you.
Okay. Dr. Vinayak graduated with a degree in physics from Bhavan's Hazarimal Somani College, Mumbai in 2007, and completed his MSc in physics at the University of Mumbai in 2009. He earned his PhD in material science from the Indian Institute of Science, Bangalore in 2015. Currently, he is an assistant professor at the School of Physics, Indian Institute of Science, Education and Research, Trivandrum, where he leads the Smart Lab. His research focuses on the electronic transport properties of nanomaterials for smart device applications, with interest in structural defect-induced transport properties of semiconductors and their applications in photothermals, thermoelectrics, and solid-state gas sensors. Dr. Vinayak has received several awards, including the Best Paper Presentation Award at a conference at Arizona State University in 2014, as a rising star in material science by the ACS in 2023 and the Inspire Faculty Award from the Department of Science and Technology, Government of India in 2016. He is a member of the Indian National Young Academy of Science in New Delhi and has been recognized for excellence in teaching at his institute. Dr. Vinayak actively promotes careers in scientific research among the college students. So now, without further delay, I just hand over the session to our guest speaker. So welcome, sir.
Thank you.
Welcome.
Thank you so much, Ms. Arul Modi.
Thank
And
you. Welcome, sir.
okay, so I'm sharing my screen, and okay, so that's the presentation. The downside of this is that I cannot see you while I speak. So the although having these online webinars and all that, it helps you in being anywhere, anytime, and so on and so forth. The downside is that it for me it gives very less connect as compared to physical talk. So I would prefer actually a physical talk, maybe sometime in future or something like that. Anyway, so I hope you can see my slides. Can you please confirm?
Um,
Sir, his
Yeah, it's
slide is
visible, sir. Okay, okay.
short,
Yes,
sir.
great.
Please click the slide.
Sorry.
Sir, slide is small,
It's
sir.
visible, sir.
Print the slide, sir.
It's visible, right? Yes or
Yeah,
no?
yeah.
Okay.
Yes,
It's
yes.
visible, but his screen is not full, sir. It's short
Screen is
screen.
not full screen, huh? Oh,
Yeah, yeah,
okay.
yeah, yeah, yeah.
Okay, I'll just stop sharing entire screen. Share. Okay. Now,
Yeah, sir, it's visible. Yeah, yeah. It's
okay.
visible.
All good.
Yeah,
Yeah.
yeah, yeah.
Yeah, that's the thing. Like when there was COVID, there was
sir, your microphone is in off.
okay. Yeah, I don't know what's happening. Okay. So, what I was saying, there were two sentences which were mostly pronounced during COVID. One is, "Am I audible?" and whether you can see me. So, the first question I have already got the answer from Miss Arul Mori. So, okay, let's start with that. At least, I particularly chose this background because I particularly wanted this audience to have a bit of a feel for what we are going to speak in this next 1 hour. Because what do you see? And tell me, what do you see in the background of this slide? Hello.
Yeah, sir, it's here. Me. Yeah.
Yeah, anybody.
Very-
Some people can write here, or you know,
Yeah, sir, it's
what do you think? What is this background?
Semiconductor material.
Semiconductor, bit more.
it's some electron proton compounds, some structural.
Some group of atoms which are just 1 feet of atom here, and there are these shiny metal contacts over here, which some are gold, some are maybe silver or platinum or something like that. Something is again in between this semiconductor and metal, there is this glass like thing. So if I, for example, this is an artistic representation, but if I, for that matter, if I could visualize and see electronic devices at such a resolution, I could have actually seen things like this. So this is what is basically all the more about semiconductor devices and device technology. And what is more interesting about it is, how do we form these things? How do we fabricate it? How does it work? That electronics is mostly taught, but what is not taught in BSc Physics Electronics or MSc Physics Electronics is how these things are made, and what are the challenges, what is the thing. And by and large, I see a lot of physics students interested in you know at least in the first few years they are more interested in cosmology, astrophysics, and things like that. By second year or third year, they are more fascinated with quantum mechanics and things like that. And that is what probably they want to do. But I'll tell you, the fact is, we also have subject which is called as condensed matter physics or materials physics and things like that, and that is entirely quantum theory of solids. Without quantum theory, we cannot explain how solid exists and it works. So the solid state physics or solid state electronics that we study is basically a quantum theory applied to multi-particles. Uh, how large is the system is basically 10 power 23 Avogadro number. That is the large number of atoms that we are dealing with in a solid state system. And then once we are dealing with such things, we try to classify them in different phases, and depending on whether their properties, crystalline properties or electronic properties or magnetic properties, there are different classes of phases. So materials are into some sort of a material zoo, we call it. Let's say, I can call it. The second part, I will try to tell you a bit about electronic devices. So from these first solid state electronics to the materials, materials to devices, devices to problems of the devices. If they are working, all good, but then what do we want more from them? Why are we still working with them? And to some extent, this last part, if I am able to touch it, I would given the time, and I'll see. Okay, but at least I'll try to cover the first two parts. Okay, the first and foremost thing is the world in which we live. I mean, the universe. Although we ourselves classify it into different disciplines like physics, chemistry, maths, biology, and things like that, nature does not discriminate itself by like that. It is for our convenience we have divided it into different subjects, right? So the nature, by nature itself, is very interdisciplinary. So which means that nature does not say, okay, I want to have this biological organism, but I will not work with mechanics of this biological organism. Like, how does it walk? How does it move? How does it hold the grip? How basically, how does it look? How does it see? How does it hear? So there is physics in all of these things, right? So it's called biomechanics. Or for example, when it comes to chemistry, chemistry will not start unless you have quantum theory of atoms and solids and so on and so forth. So to have those orbitals, bondings, the intersection of, the bonding between the atoms where there is a wave function overlap, it's all chemistry, physics applied to chemistry, where you say quantum theory of bonds and things like that. So nature itself is very interdisciplinary. It has physics, chemistry, to some extent electronics now, which we are going to see, and to a large extent which will also see data science or mathematics or statistics, applied statistics, whatever you call it. It is that computer science. So all of this, a large umbrella is called data science for that matter. What do? We will have, when it comes to electronic devices, it's absolutely interdisciplinary, where we need to work around with all of these physical properties: electric or magnetic signal, pressures, flows, chemical compositions, acoustic or sound wave vibrations, humidity or moisture, temperature, motion, acceleration, vision like optics, and so on and so forth. So these are things where we are making electronic devices for, right? For example, so when it comes to semiconductor devices or semiconductor, these are the electronic devices. I'm sure all of you are carrying this piece of silicon in your hand right now, or in your pocket. So it is just that now it is occupying our lives. So how do we start making things? How did we start making electronic devices? So to get that answer, we have to actually go back to the times where man actually started making things by hands. Like, so when did man actually started making new stuff? Now when I say new stuff, means something which did not naturally exist. Okay, now any example would be your vehicle, your wheel, your electronic device, your table, chair, whatever it is, it's man-made. They do not grow on the tree, right? So it does not exist in nature just like that. So to have that answer, we have to look back in time, and typically, like, in these times where people, when men and women were working with naturally existing materials, and around 5000 or something, they found this thing called fire, and with that they started making things like alloys or glasses. Okay, take sand, silica, melt it, and then heat it, and then make it becomes transparent. It gives you quartz or something like that. So man discovered that you can use this fire and you can use these things to make new things which do not exist in nature. So that is typically a timeline of 5000 before Christ. And now we are in 2000 years after Christ, right? So typically 7000 years is what man has been making a lot of stuff. So this is probably the time where man started making things by themselves. And this was probably, you may have seen this picture in your history books or books on prehistoric man and things like that, where they are making and melting things. Had there been some very hi-fi journal at that time, the first paper would have been melting tin and copper together can produce more harder metals for alloys. And what was the use of those alloys? They were used for making tools for making, cutting, for wars and for archeries and things like that, very sharp alloys and things. So that could have been the first big impact paper of times, if had man been publishing at that time. So this thing of making new things by ourselves is actually very new. And I mean, compared to the existence of earth, compared to the existence of man and things like that. Okay, so we initially started with stone age. We went into some sort of alloys, bronze, iron, steel, and then this is probably the onset where man started making things by himself. And today this is where we are in electronic technology world, where we are making things by ourselves for silicon, okay, using silicon. So there is this discrimination between, so the first thing, for example, this thing of melting these two things together, is it discovery or is it an innovation? What do you call it? Any
Innovation.
answers? Why innovation?
Because these metals already existed in the earth
Hmm. The metals
and we
existed,
made.
but the alloy did not exist. So something which does not exist, when we make it, it is called as an innovation. You have to put your idea, you have to put your design. So somebody had this idea, yes, I can add these two things and that will become a third alloy, okay, which will have a very different properties or things like that. So discovery is something which is existing there and which is found. Like for example, discovery of a star, discovery of an element, discovery of any naturally existing stone or mineral and things like that. So this is where you make innovation, you make new design. So these two things actually go hand in hand. So you have discovery and you also have innovation. They have proven to be very, very important for mankind, because it is something which has driven our society for long. For example, magnetic materials were discovered, magnets were discovered, iron, cobalt, nickel. But then magnetic random access memories were innovated. So somebody took this magnetic material and then made a magnetic ram storage device, hard disk, right? Similarly, somebody found semiconductors and somebody made diodes, triodes, and electronic devices out of it. So the discovery is something which is absolutely essential. We need to have it, and without that we cannot have more innovations possible. Okay, so while perhaps most of the material development was triggered by concrete applications in mind, the curiosity driven search and attentive observation used to play a role. Like for example, the first thing which led to this discovery of magnetic materials or discovery of semiconductors did not know what am I going to discover, right? It was most of the time a serendipity or something like that. But then the innovation had a fair idea of what he or she wanted, so that was driven by an application. So if I show you this chart, for example, for magnetic memories, hard drives, which we use now, right? So earlier, sometime in 1930s, somebody discovered alnico alloy and showed that yes, it will have a substantial amount of magnetic energy storage, right? And then for a long time, people tried to improve its magnetic energy storage. While in 1960, somebody discovered samarium cobalt alloy, which had itself higher capability of storage. So then a small gradual change for some time. Again, somebody found this neodymium iron alloy, which had even higher magnetic moment storage. So there was discovery of something which led to further innovation. So both are important, finding new things and putting them to task. So both are a part of the deal. So
Sir, sorry
somebody
for the
wants to
interrupt.
say, yes, please.
Sir, screen is not sharing. Sir, screen is not changing. Only screen in display. First slide. You
Really?
have
Hello?
not? Yeah, sir. Yeah.
Is it visible now?
Slide is visible, but it is not moving.
Oh, I don't know what is happening. I'll stop presenting. Oh, I was thinking all the while that it is presenting. Can you see now? Hello?
Yes.
Yeah, yeah, sir. Yeah. Now it's start working. Yeah.
But if I put it to slideshow, can you see now?
Yeah, sir. So, yeah. It's visible.
Oh, this is what I have been showing. I thought, oh, so you were all the while on this slide, is it? Okay.
Yeah. Sir. This right only.
Okay,
Yeah.
so what I spoke is this is a very interdisciplinary world. We are making electronic devices for most of the physical quantities here. Okay, how did man started working, finding new things is this timeline, and typically by this time man started to make things by himself or herself. That is around 5000 before Christ, and all the while now we have been making new things. And at the moment we have these discoveries like integrated circuits, diamonds, artificial diamonds, high temperature superconductors. So this picture you may have seen in your history books and things like that. And then this could have been a most striking or the most breakthrough discovery. And currently we are here in the silicon age. So I was telling about this discovery versus innovation, and what I told is magnetic materials are discovered while magnetic storage memories are innovated. So for example, if you can see this plot, every time there is a discovery of new compound having higher magnetic storage capability, there is a step jump in the performance of the magnetic storage devices. Okay, and once that is discovered, there is a gradual or incremental change in the performance. But then to have a bigger better performance, you need this breakthrough from the discovery that there will be something which will have a higher storage capability. I hope now you can see, right? Please confirm.
Yeah, sir. It's visible. Yeah. It's
Yes,
changing.
yes. So this is what is my first thing. Okay, now let us come to solid state electronics. Like since the topic is about making material innovation through semiconductor fabrication. Okay, so we need to know first few things from the solid state electronics. So somebody had innovated that you take a metallic two electrodes, put them inside vacuum and apply a very large electric field between them and put in some sort of a gas inside that vacuum tube. The gas will ionize and it will hit one of the thing, and it will the electrons will be ejected because of the electric field, and they will travel to the other positive electrode. So that is called as a vacuum tube diode. So depending on certain striking voltage, there will be a current, and that the vacuum tubes were used like that. Similarly, somebody can hold a third metallic electrode in between, which is more positively or negatively biased, which can control this flow of electron going towards the anode, which is like a transistor. So what is transistor? Basically a switch where the flow from collector to emitter is controlled with a base current. Okay. So earlier vacuum diodes, which were like this much bulkier and power consuming thing, used to heat up a lot, they were gone to this small device just because of the improvement in understanding of solid state physics. Okay. I hope there are no messages here, or there are any. Right. So we could go from here to here because we could understand better solid state physics. Okay. So what does that mean? So if you look at any crystal structure of materials, we can, depending on their electronic properties, whether it can conduct, it cannot conduct, or it can conduct after certain voltage or temperature, is called as a conductor, dielectric, or insulators, and semiconductors. There is one more kind which is called superconductors, which are like with almost zero resistance at very, very low temperatures, but it's a very different beast. It cannot be explained with trivial quantum mechanics. Okay. Materials. So any material, if I take in the universe, I should be able to classify it in these four classes. Again, there is a message. Somebody raised a hand, please. Yes. Yeah, you may ask your question, please. Hello. Somebody raised their hand, I think.
Sir, yeah, continue, sir. It's
Okay,
responsible.
fine. So it came from, so that knowledge of different electronic components was useful in making complicated electronic structures. So the first thing where diodes were used was to make rectifying junctions for transmitting radio signals and things like that. And now we have, like, a large class of electronic devices which are there, which are made using knowledge from solid state physics, knowledge from bit of a chemistry, and knowledge from electronics and mathematics. Okay. So wherever there are sensors, so how do we make them? We make them by this lithography. I'll come back to this in a minute. I'm sorry. Okay. Yeah, let's go by the flow, whatever it is. Okay. So how do we make these things? We first, so what we use is something which is called as lithography. Okay. Lithography is a process by which semiconductor devices are made, fabrication is done. Okay. So whatever diode is shown to you, that you write its IV in, for example, I mean, sorry, I'll write here, pen. So normally you draw your diode like this, and there is a P and N side, and you bias this junction and all that. How do we make a diode? We don't really take a P block, N block, and fuse them with a glue or something. No, that's not how we make it. The way we make a diode is, the process is called fabrication process of semiconductors. Diode is just an example. A lot of all those devices which I told you is that. What we use there is called lithography. Lithography, you can, lithos is a Latin word. I think it means stone, and so it's like carving stones. Or charge particle beam or light or whatever, soft, some sort of probes to make it, and that's how we fabricate device. So broadly I can classify this fabrication into two ways. One is a top down method, like I start with a block of wood and start carving it into a table like that. So there is you take a stone and you start cutting it smaller and smaller, and you make some smaller structure. The other way of solutions, to start from atoms, molecules, grow from vapors, grow from solutions and things like that. That is a bottom up approach. So there are two kinds of approaches which are followed in semiconductor fabrication, and as a result we will have something which is like this. So this is a typical example of a MOSFET. Okay, MOSFET, you know, metal oxide semiconductor field effect transistor. So where you will have a semiconductor channel, where you will have a gate, and where you will have a oxide layer underneath the gate to control the conductivity of this channel. But how do I make? I mean, if you remember your diagram, for example, JFET, I draw junction field effect transistor, it will show you something like this. If this is N, it will show you this is P, and there is possibly a gate over here, and they will kind of bias the junction like this, and from
Sir,
here to, sorry, yes,
sir, sorry for interrupt. Sir, your drawing is not visible, sir. It's only slide on the screen.
drawing is not visible.
Yeah, yeah. And
Oh,
slide is not moving, sir.
you can see this slide of top
Yes,
down
the
fabrication.
yes, the electronic materials, so it's visible, sir. But
You are there only. I don't know what is happening. Do you see this slide now?
Yes, Nidhu.
This
no,
is
sir, it's
problem
not.
for this online talks. Yeah.
Yeah,
Hmm. Do you see this slide, top down fabrication?
yes, yeah, sir. Now it's visible. Yeah, top down nanofabrication in on screen, sir.
Okay, I'll continue like this. I hope this will just,
Yeah,
let's
sir.
go
You will
ahead like
change
this.
next slide. You will change, sir, and I will check it.
I will not draw anything. Okay, fine. So if you remember your drawing from your books, it will be just some sort of a block, and that block will be shown to have some pocket of P type and N type. But that's not how we make it. We make it by techniques called as lithography, which is patterning, thin film deposition, which is like additive step. So you add some material and you etch, you subtract something, which is called as a etching process or subtractive process. So there are various of these processes for making it. Okay, so one is thin film depositions can have various kind of physical or chemical vapor depositions, and the etching is some sort of reactive ion etching, wet etching, and so on like that. So what do? We use this light. Okay, so for example, there is a light source and you hold your hand in front of it. What will it do? It will cast a shadow of your hand onto the screen or the wall, right? So in that case, if I use a magnification system, I can magnify or demagnify this shadow to very small length scales, right? So that is exactly what we do. We first make a mask of whatever we want. So that mask is like your hand, which is in between the light source and the screen where you want to project it. And we use lens system to magnify and demagnify it to from this size to this smaller size, which is called as a demagnification thing. So this is what is we do in photolithography. So we start with light and we make much smaller shadows of it using lens based magnification system. Now, why light and what is light doing? So what we do, what is written here, which is called a resist, is basically a monomer which gets polymerized when you use appropriate light of appropriate frequency or wavelength. So normally we use something which is close to UV or 200 to 300 nanometer, because that is suitable for polymerization. Okay, also this then practically limits some sort of a limit on the fabrication size, because you cannot have feature size smaller than the order of wavelength, because diffraction effect starts to come into the picture and you can't make demagnify further, right? So in that case we can't use light anymore. What we use in that case is electrons or electron beam, which is called as here charge particle beam lithography, where we use electron beam. Why? Because now if I want to make smaller structures, I need to have wavelengths which are smaller than 100 nanometer or something like that, right? So it is not possible to use something which is in this ultra high energy, because these are very strongly interacting radiations with the matter. They will ionize. Still it is not moving.
Yeah, sir. It's visible, sir.
So
Sometimes this issue, sir. You will change the slide. You will tell me, sir. I will Yes or no in slide is sharing. Okay, sir.
Okay,
Yeah.
okay.
You check in
I'll
again.
just
Change the
hope.
slide. It will tell you. I will check it and I will yes or no. It's slide changing.
I think my Wi-Fi is stable, but I don't know why is this issue. But yeah,
Some issues in Google. Yes, sir. Issues in Google Meet. Problem. It's not sure, sir.
yeah, that's how yeah it goes. Okay, so we use electron beams. Now what do we do with electron beam? How come electron beams have wavelengths which are smaller than the light? Is because electron is a particle which will show you wave particle duality nature. So when we consider it as a wave, it will have a wavelength which will be proportional to the energy of the electron. So we basically start with some high voltage, accelerate it with high voltages so that it will gain enough kinetic energy, and that kinetic energy will correspond to a certain wavelength. That would be the thing. So likewise we use these lithography steps to make features like these. So this small feature is, let's say, 50 nanometer or 100 nanometer width. Just to make that, we need to use this kind of lithographic techniques. Okay, so then using that we make whole lot of other devices which gets into electronic device and things like that. So what do? We then make a lot of structures which can be used into these semiconductor device fabrication, because what it requires, for example, here is that you need a silicon layer which is highly doped. Then you need a silicon layer which is highly doped with n-type carriers. Here it is doped with p-type carriers, right? So first we start with silicon, do ion bombarding of some kind. You need not to use silicon also. There will be other materials also which will be of interest, like for example gallium arsenide, gallium indium arsenide, gallium phosphide, algan, all sort of things. And currently we are going into two dimensional materials and things like that. Okay, so now with that we will make these devices which will be having its own use for various electronic applications, something which will be used in high power electronics, something which will be used in micro electromechanical devices which are like sensors, actuators and things like that, something which will be used in light based photonics based things where you control the propagation of light in these material from second order, order harmonic generations, lasing, wave guides and things like that, optical transceivers, could be silicon, it could be 2 3 compound semiconductors, it could be compound elemental semiconductors and alloys and things like that. We also use it for memory of magnetic memory storage. So when you couple semiconductors with materials which have magnetic moment like ferromagnets, then or antiferromagnets, then by application of magnetic field you can switch the polarity of the spin and you can record the spin as a information. Up spin is 1, down spin is 0. So you call it as memory storage for magnetic memory storage devices, which is called spintronics. So for spintronics again we need semiconductor devices plus additionally having magnetic capabilities. And then there are things which work at wireless technologies or RF, radio frequency propagations, which will be like your wireless communications and things like that, all your 5G 6G networks, radars, waves, microwaves, packaging of those devices, everything will be, so again there you will need something which is able to transmit this radio frequency signal and something which is able to receive this radio frequency signal. So antennas and receivers, these are also made of semiconductor devices using the same processes of semiconductor device technologies. And now where we are going into is some more efficient sensors, something similar to your for example, when COVID broke, initially we used to do RT-PCR, but then there came antigen test where you could put your sample of blood and then it was functionalized with some sort of biomolecule, and that biomolecule will interact and it will give you some sort of electrical signal which you record. So there are more efficient sensors, there are more efficient batteries with higher charge storages, There are nanomaterials which are making your computer chips much more faster. Earlier we used to have single core, then it came dual core, then came quad core, because we there came a limit on the transistors that you can't increase the switching frequency of transistor. Then if I can't increase switching frequency, let me divide my task into several cores of the processor and let me do parallel processing, and that's how we get more faster and faster computers now. So 5 i5 i7, like so many cores are there, because there is an inherent ability or inability of transistors cannot switch beyond a certain frequency. Now, why? Because they are limited by all this regime of quantum transport. You are coming to such a low and low range where the devices are getting so much smaller that quantum mechanics is getting so much dominant that earlier where you wanted current to go, which will be on state, and current to stop, which will be off state, but now you are at such a small length scale that there is something which is called as tunneling current. So even without application of electric field, the electron can tunnel through a particular barrier, and that is the range where we are in nanoscale now, and that is why we cannot make feature sizes much smaller than that. Okay, so we are limited by that. So now in the nanoscale things where we are, so for example, if you remember, the typical diameter of a single atom is of the order of 0.1 nanometer. So if I take 1 nanometer, that will be like about putting 10 atoms together. 10 nanometer is like 100 atoms together in a row. Like, so we are in a regime where we are getting close to atomic regime from bulk, right? So that is the problem where we are leading to right now. So what are the structural differences that happen in nanoscale? Because is it, so if I go on reducing the length like this from bulk 1 millimeter to 100 micron, 10 micron, 1 micron, 100 nanometer, will my atoms or group of atoms which was behaving in a certain way when they were too many in number in bulk, do they also behave in the same way when they are few in number? And the answer is no, they do not behave in the same fashion. Nanoscale materials have very different properties compared to the materials which was in their bulk. So why does it happen? Just purely because now you are in a regime where you are dealing with several atoms and not large group of atoms, where quantum mechanics is dominant. Okay, and that leads to some sort of a special confinement, that also leads to, because now most of the atoms are on the surface, and because of that the chemical bonds are somewhat uncompensated, that also leads to these problems. So what properties are affected because of this, and how can we tune them? That is a question to ask. For example, if you take this butterfly and if you put it under microscope, you will see structures like this. Okay, and this is more and more you go on magnifying, you will see structures which are ordered on the scale of nanoscale, and that is something which is giving these colors to butterfly. So butterfly color is not something because there is a electron which is making a downward transition from a higher energy level to a lower energy level and emitting a photon of a certain wavelength. No, it is, let's say you put
Sir,
white light
sir,
on, yes,
sir, slide is your slide is visible for number. So 15. Yeah, sir.
you are on
Sir,
15.
sometimes it's not. Yes, sir. It's 15 on now. I now change you are 20%. But you are listening, but you are audible, but not screening. Now in screen is changed.
Right, now you can see.
Yeah, sir.
Okay, can you see the structure on the screen?
Yeah, sir. Yeah.
Yeah, so those are like structures. If you look any biological organism which is sharply reflecting colors, and not only color reflecting, if you change your angle of viewing, the color will change. Like some bugs are very shiny green, but you put them on your palm and then you change your angle at which you are seeing, those green bugs will appear somewhat orange, brown, and things like that. So that is because they are undergoing reflection of light of different wavelengths, because at different angle it sees different periodicity. So various things happen. For this was an example what happens at nanoscale, like photonic crystals, surface plasmons, quantum dot fluorescence. These are some of the examples, and each of them is, so what I'm showing right now is an example of a photonic crystal. So it's a crystal for photons. Like if we are talking of solid state physics crystal, those are for crystal for electrons. This is a crystal for photons. Then you will have some sort of a confinement effect when you reduce the dimensions from 3 dimensions to 2 dimension, 2 dimension to 1 dimension, 1 dimension to 0 dimension. What does that mean? That how many dimensions are there in the nanoscale? So this is few nanometer and everything else is, let's say, few micrometers or more than that. Then it is 2D. Then 2 dimensions are in nanometer and 1 dimension is micrometer or more, it's 1D. And then all the dimensions are in nanometer, then it's kind of quantum dot QD. Okay, 0D. What changes is basically the way electrons can move inside this structure. Okay, not initially when we have an insulator or a semiconductor, it has a band gap. It has a band gap. I hope you can see now.
Yes, sir. Yeah, sir.
Hmm.
Yeah.
So you take a bulk semiconductor, it will have a conduction band, valence band, and it will have a band gap. The moment you have made a two-dimensional quantum well or a two-dimensional analog of that semiconductor, this band structure will change like a step. So in that case, you will have electrons cannot have even this much energy. The minimum electron energy will be the flat lines. When you go to 1D, it will become like this, sharp lines, and 0D, it will be just this lines. So in practice, what is happening is that you are cutting off certain amount of electrons, or you are saying that electrons cannot have certain energy. So your band gaps are changing completely from 3 dimensional to 2 dimension and so on. And inside the crystal, I mean, I can tell if those who are interested, PhD students or whatever, it's a k wave vector dependent change. So there is a quantization of k wave vector for every dimensionality change. Okay, so that is how we see. So we start from very large continuous bulk material. You may have a metal where there is half filled and half empty, but there is no band gap, right? But from bulk, if you come to length scales of few thousands of nanometers or few hundreds of nanometers, sorry, that is mesoscopic scale, where energy will start changing like these linear gaps, you know. So like an atom, there will be sharp energy levels at some point of time, and when you are in the range of few atoms, you will have some gap which is arising even inside metals. Okay, so you will have, just because you have changed the size, certain metals will become like an insulator. Okay, so that is how that is one of the way it happens. Now we are in the region where with time, as it increasing, we are packing too many transistors in the same length scale, which means that we are reducing the amount length per transistor, and that is what is happening, and beyond that we cannot go. Okay, so there will be a law where so there is a cartoon here. This cartoon shows that, you know, for example, 10 years or 20 years ago, you might be very young, but for example, if you have handled computers 10 years ago, you were okay with the speed that you used to get. But now, even if it doesn't show up things in few seconds, you get frustrated. So if it doesn't show up things, you will get frustrated. So our patience is also reducing over time, not just the density of transistor or the speed is increasing, but like that. I mean, so basically with time, what we are doing is we are getting more into nanoscale structures over time. And what is happening, I mean, what is the material innovation part here? I mean, you can basically see that with the help of those nanofabrication technologies, for example, like this, you are putting various materials together which did not exist naturally, right? So transistor itself did not exist naturally, and now we are making more complicated structures like these, where What is the thing? Somebody, is there a? Okay, there are questions. Okay.
Sir, you change the slide, you will tell you, sir. I will correct it's change or not, I will tell you, sir.
Yeah. Okay. So what we can see here is that, I hope you can see this.
Yes, the channel length is
Channel
decreased.
length you can see. So you see
Yeah.
that transistor, the time is increasing, transistor dimensions are decreasing, and now we are almost in the range where we just need one single atom thick, just one atom thick layers, which is two-dimensional layer. Okay, and that is where we are going. So if you look at the amount of scales, what earlier we used to do from 65 to now, we have come down to 5 nanometer thick chip design in terms of semiconductor fabrication, and that has also increased cost. Okay, cost of fabrication, for example, this, the blue line, which is increasing over time. So yes, we need to have various kind of strategies and things like that. Now with the AI and all that, probably we'll be able to mitigate some of the challenges in fabrication. Not only in application, but even in fabrication, AI will be useful for somewhat optimizing the structures and things like that. So we are going into this two-dimensional atom based. So what do you mean by two dimension? Just one atom thick. The thickness is one atom, that's it. You can imagine like a sheet, like a bed sheet, which is made up of one single atoms. So now people are making electronic devices with such kind of sheets, and this is a typical chart of timeline of when we can actually expect devices based on single atom thick sheets. Okay, so typically growth, transfer, interface, these are all processes of semiconductor fabrication, and they are happening. And by, let's say, 2024, where we are already now, we should be having a two-dimensional technology on CMOS, a semiconductor metal oxide semiconductor device fabrication based on that already here with us. So that is the idea. I think I'll stop here. The content is quite a lot, but yeah. So excuse me for this. I think this is, I would say, I would try to leave you with this, that it is very futuristic, that in semiconductor fabrication, we are basically growing things which does not exist naturally, and that allows us to have innovation in fabrication. And it is now you are limited with your own design. What can you actually make by making new structure which will have new application? Okay, so first of all, somebody now recently somebody recently in 2004 figured out or discovered graphene, which is single atom thick sheet of carbon. And from graphene, graphite, when we have a pencil, lead pencil, right, which is having graphite, when we write, it goes on leaving these 2D sheets of graphene, thicker one, but it does that. Okay, so you can easily exfoliate such top sheet of atom from graphite, which is called as graphene. And then chemists made different kinds of carbon atom thick single atom sheets, which are graphene oxide or hexagonal boron nitride, which is similar to graphene but made up of boron and nitrogen, no carbon. Then people came up with 2D, two-dimensional chalcogenide materials, which are like molybdenum disilicides. These are graphene is a zero band gap Dirac semi-metal, zero gap thing with Dirac fermions and all kinds of, what they predicted in quantum mechanics, they could all find those kind of charge particles in graphene. So that's why it was more exciting for basic physics also. And then people discovered these transition metal dichalcogenides, which are more higher band gap, more spin orbit coupling, more newer things, topological materials, where topology plays a lot of role in electronic devices. Topology means something which is just protected by its topology. Okay, so electrons will have more conducting things on the surface and non-conducting thing in the bulk and so on. And then making two-dimensional oxides, which can make two-dimensional dielectrics and things like that. So all sort of things which came up after that, and now we are working with all of these two-dimensional things to make semiconductor devices out of two-dimensional materials. So that is what I'm saying, that one can have material innovation, and through material innovation one can have semiconductor device fabrication, which will get to next level of fabrication. Okay, so with that I think I'll stop here. This is my
So
lab members.
slide is not changing, sir, because the
Right.
channel length size issue is freeze, but not changing in slide.
Okay, so you couldn't see after that.
Uh, Yes, sir. Now, sir. Yeah, now see, sir.
Okay, sorry,
Yeah,
I'll just
well,
quickly show you here.
but you
After
have
this, yeah, this is something which I showed, cost of chip fabrication as the size goes down. The blue one is basically the cost, which is increasing over time because we are going smaller and smaller in dimensions. Okay, that is one. And the other point is that now we can use various AI based strategies to bring down this cost and to optimize our fabrication. Okay, I hope you can see this slide. Okay, so that's also how AI can enable. And this is basically a tree of layered materials, like layers, just single atom thick sheet of atoms which is used. Okay, earlier they were predicted that they cannot be thermodynamically stable, but in 2004 these two gentlemen, Andre Geim and Novoselov, they discovered single atom thick sheet of carbon, and then that's how graphene was discovered. And with graphene came various lots of two-dimensional materials which can be used in electronic devices. You can see this, right?
sir. The slide number is 32. I mentioned. Yeah.
33.
Yeah, sir. So you play in slide visible in option F5. You show.
I think I'm done. Let's just yeah, I think I'll take questions and I'll try to answer them. Yeah, that's fine.
Yeah, sir.
I'm sorry for that. You can't go
Yeah.
beyond the point. Yes.
Sir, only I visible in only 5 slides. I visible, but you are audible to
Okay.
listen. It's not visible for every slide. Only I use 5 slides. I will watch it.
Oh, okay. I'm sorry for that, but I don't know. Is it a it is a problem? Can you see now? Okay, I'll just quickly
Uh,
glance through all that. Can
yes,
you
sir.
see now?
Now, yes, sir. Can I see in smart lab in visible for?
Sorry,
Sir, visible for smart lab in screen now.
visible for
Smart lab.
oh that last slide.
Yeah, yeah, yeah.
No, but I don't know what is happening. I have shared my screen. I don't know what is happening. Hello,
Yeah, sir.
is it visible now?
Yeah, sir. It's, first slide is visible. Yeah, second. So,
Okay, I
can,
will just
can
go
you
to
share?
that thing. I'll quickly run through the slide. It is a flop show. Yeah, from here. Can you see?
Sir, can you see in channel length scaling issue?
Yes. Now this is a slide which I was showing for
Yeah, sir.
cost.
Cost for
As your
chip
size
design.
goes down, your cost of the fabrication goes up.
Yes.
Okay. And now we are in the node of 5 nanometers. So that cost is like huge. To bring down this, they are doing all sort of material innovations as well as AI to help mitigate all these problems. You can see this.
Yes, sir. Our research indicates the 6 inheribles. Yeah, the
This
two-dimensional.
two-dimensional nanomaterial.
Yeah, yeah. Exchanges, sir. Yeah.
Okay, this is what I was saying. Initially, they were predicted not to be stable, but then in 2004, these two gentlemen discovered graphene, and after that, there was this whole lot of series of materials which were discovered, and now we are into making devices with these two-dimensional layered materials which are single atom thick. And this is a typical timeline of projected timeline for having two-dimensional material based devices a reality. Okay, so it includes all kinds of fabrication processes which I briefly told you during lithography stages: growth, transfer, interface, contact, design, and all kind of things. By 2000 24 we were expecting rollout of design with integration kits, and it is probably at lab scale. It will come soon. It will soon become reality, and that's how it is. And with that, I would like to conclude. Can you see this?
Yes, sir.
Yeah, sir. Can I see?
Yeah, so
I
I
am
would like to
unable
thank
to.
all of you
Sir,
for giving me this opportunity,
sir,
and I'm
sorry for
really
the
sorry
interruption,
for.
sir.
Hello.
Sir, sorry for the interruption, sir. I
No,
encourage
no,
each
I'm
of you.
really sorry. Uh,
I
I am
encourage
sorry.
each of
Maybe
you.
my internet connection is weak. Yeah.
Yeah, sir. I
I
Okay.
have
encourage each
Yes.
of
requested.
you to ask any
Can I
questions
have?
related to the lecture. Sir will be happy to
Yeah, we
answer
can
the.
take the question. Sure. I don't know what was the problem.
I encourage each of you to ask any questions related to the lecture. Sir will be happy to answer them.
Can I ask one question?
Sure. Go ahead, please.
Yeah. How can I use artificial intelligence for making best
Fabrication.
this?
Yeah.
How
So
far it is easy? Because
no,
we
no.
are
So
physicists.
first of all, I'll tell you one thing. I mean, just before making any device or anything, we do some sort of a modeling to see how, well, what will be the outcome nearby, right? But then, if you have large set of data where there are large set of permutations, combinations, and large set of outcomes which are possible, which becomes very difficult for humans to process that amount of data. So in that case, one should employ AI. First, we start with first principle techniques, quantum mechanics based methods, to start with single DFT, density functional calculations, and then outcome of those density functional calculations is been fed to AI, so that it will try to converge onto first few compositions or first few ways of making it. So for example, if there are failures of some kind in the fabrication process also, you do some structured set of experiments and give that data to AI. AI will try to find correlations and decorrelations, and try to tell you what must be going wrong, or at what stages optimization is required. So you first train your algorithm with enough data, and then ask the algorithm to predict, and then that way you will be able to avoid a large set of experimental outcome and empirical optimization.
Okay. As a physicist, it is easy to write the algorithm.
Yes, and everything comes, I mean, should be taken with a pinch of salt. So even that AI outcome, we have to make robust algorithm so that it will have robust predictions. So most of research now is going into reliability, optimization of AI. Yeah, anybody else? Hello, can you hear me?
Yes, sir.
Yes, yes.
Yeah, I think I'll save my bandwidth by reducing my video. Okay. Yeah. Anybody else? Yeah, I can probably give more precise talk on something. This was very general because I knew there was a very general audience. But if it is for PhD students, then we can start with a technical topic and then talk about it. So, how things are done and so on, like that. So for example, fabrication process itself, or how properties change with 2 dimensions, 3 dimensions, and things like that. We can take specific example of just the electron. So for example, in the electronic device, you need conducting wires, right? So when you make a circuit, there is not only the electronic element, there are these wires also. Now, when you are making integrated circuits, between those transistors, there are interconnects. Now, these interconnects are also getting smaller and smaller. So the bigger problem of electronic device is not about the devices themselves, but the metallic interconnects. Because at such a small length scale, the resistance become very, very high. Okay, and it is no longer metallic. So if it is no longer metallic, how will you have a zero potential or minimum potential drop between the two things, right? So now people are also trying to find out ways of finding metallic interconnects like carbon nanotubes and things like that. I will try to share the PPT. Let me see. Yeah. Hello, can you hear me?
Yes, sir.
Yeah, are there any more questions?
No, sir.
If okay, then we can, yeah, conclude maybe.
Sir, we can conclude. Thank you so much. On behalf of the department, let me
I
thank you.
am bit of a dis, unhappy with my connection.
Yeah,
That's why, but I hope sometime we. That's why I prefer physical talks. But
yeah.
anyway, let's see.
Thank
So
you. On
yeah,
behalf of the
technology,
department, let
relying
me
on
thank you
technology.
profusely for accepting our invitation. Go to Madesh. Madesh again.
Thank you,
I
sir,
would like,
for
I would
accelerating
like to add
insights.
one
Yes,
thing. I would like
yes,
to add
Madesh.
one thing. Just
Yes,
one
sir.
thing. Typically in physics course, BSc physics course, MSc physics course, people are not given this feel for this subject, and that is also the reason that they are not attracted towards this. It is very easy to get attracted by cosmology, astrophysics, and quantum mechanics and things like that. Unless they have this feel for this subject, they will not develop an interest. So that is why also we should have more such talks where they will have different flavors of other flavors of physics, so that they will know what other areas are there and what they can do.
Sure, sir. Thank you. Thank you.
Thank you, sir, for accelerating insights. Your lecture promises to be an enlightening and intellectually stimulating experience for all of us. So, Thanksgiving is a time of awareness and gratitude. So, I'd like to invite Subadev to express the vote of thanks. On behalf of our Astronomy and Innovative Forum, I deem it a great honor and privilege to propose the vote of thanks on this memorable occasion. I take this opportunity to express my deepest sense of gratitude to our speaker, Dr. Vinayak, who spared time from his busiest schedule to grace this occasion for his valuable insights in the field of material science. Sir, we wish to collaborate with you more in the future endeavors. I thank Loyola College Management for permitting us and for supporting us. Next, I thank our dear HOD, Dr. Madhavan, who supported generously to make this event a resounding success. My heartfelt thanks to our forum in charge, Dr. Arunmoli, and our mentor, Dr. Dinesh Raja, for their constant guidance and encouragement. I thank all the staff and non-teaching staff of the physics department for helping and supporting us. I thank our technical team for the tireless effort in making this event an astounding reality and for the smooth functioning of this event. I also thank our forum members who gave their efforts to achieve this success. Last but not least, I thank all the participants who attended this lecture, and I hope this lecture would have enlarged your vision and knowledge. Thank you once again.
So thank you very much, sir. We'll conclude. Thank you.
So thank you so much, sir.
Okay, bye bye. Okay, see you sometime.
There is a feedback
feedback form in the chat, so please fill it for your certificate.
Thank you.
Next,
Those who have doubts, they can write to me in email.
Yes, sir. Sure. Sure. We will collate and we will try to put it up so that we can get the answer.
Put
Thank
my
you.
mail ID in the message.
Yeah. Thank you. Thank you.
Okay. Got it. Please.
Bye. So my appreciation to the organizers, right? Well done, right? Very good. Happy that things went well, right? Bye. Good night.
Thank you for joining us today and hope to meet you all in this webinar.
Yeah. Good night. Thanks. Very good.